Dr. Hubbard worked an example on graphing using all the knowledge that we've gained from the first derivative and the second derivative information. And he used, he graphed an example with rational functions and one with exponential functions. So I thought I'd pick one having to do with trig functions to supplement our arsenal of examples. I think I'll do this number 44, y equals sine x plus cosine x on the interval from 0 to 2 pi. And our directions are to sketch the graph over the given interval with all the transition points indicated. If I don't know what a transition point is, where do I go to find that? Yeah, I know you guys are probably thinking the textbook. That's right. On page 236 in the summary of section 4.6 is the description of what a transition point, and the definition of it is earlier in the section. It's a point in the domain of the function where either the first or the second derivative changes sign. So we're really just looking for those critical numbers of the first derivative and zeros of the second derivative. All right, our example was y equals sine of x plus cosine of x on the interval from 0 to 2 pi. And we have to indicate transition points, so I'll just write that briefly. So the transition points are places where the first or second derivative is equal to 0, where the first or second derivative changes sign. And we find those places by setting the first or second derivative equal to 0. So, in other words, we need the first and the second derivative for this function y. So let's find y prime. Derivative of sine is cosine x. Derivative of cosine is negative sine x, so I'll just go ahead and write that as minus sine x. And then y double prime, or the second derivative, is the derivative of the first derivative. So that's negative sine x minus the derivative of sine x is cosine x. Okay, so there's my first and my second derivative. So let's set y prime equal to 0 to find the critical numbers. Okay, so y prime was cosine x minus the sine of x. And we're going to set that equal to 0. In other words, we're going to try and find where the cosine of x is equal to the sine of x. And you can solve that any number of ways. You can use your unit circle knowledge, and I think that's what I'm going to do. So I'm going to use my unit circle knowledge to figure that out. All right, where is the cosine ratio equal to the sine ratio on the unit circle? That happens here when first and second coordinates are root 2 over 2. And down here in quadrant 3, when first and second coordinates are negative root 2 over 2, both of them are negative root 2 over 2. So x is the angle there. So x is going to be pi over 4. And then this angle down here in quadrant 3 is slightly bigger than pi. It's a quarter more than pi. That one's going to be 5 pi over 4. So those are my critical numbers. And so then what I'm going to do is I'm going to find the extrema using the first derivative. Using the first derivative test. And I like to have some sort of a representation of the real line. In this case, I don't need the whole real line. I'll just use the interval from 0 to 2 pi. And I'll just give myself some scale. And what I'm really interested in, my first derivative is equal to 0 at these two x values. And so it's going to possibly change sign on either side of those. Pi over 4 is here. And 5 pi over 4 is between 4 pi over 4 and 6 pi over 4. So I like to draw myself these little imaginary extensions of the real line to let myself know I'm interested in the secant sign of the first derivative here, here, and here. And just to make clear what I'm looking for, I'm looking for the sine of y prime. So I'm going to pick a value in between 0 and pi over 4 to see what the SIGN sign of y prime is. Or I could think about it reasonably, looking on this unit circle. Let's just say if this angle is pi over 4, then about here would be pi over 8, and my cosine coordinate, which is my x-coordinate, is bigger than my sine coordinate. So when I do cosine of x minus sine of x, I get something that's positive. You can also pop pi over 8 into each of these values in the first derivative, because we're looking for the sine of y prime, and verify that we get something that's positive. So I'll just write a little note here that I'm mentally checking at pi over 8. In this second interval, I'll check at pi. Cosine of pi is -1. Sine of pi is 0. So -1 minus 0 is something that's negative. And then I'll check here in this interval from 5 pi over 4 to where we are to stop graphing at 2 pi. I'll check cosine of 3 pi over 2 minus sine of 3 pi over 2, remembering each time I'm checking the sign of the first derivative at a number in this interval determined by the interval that we're given and by the critical numbers. So if I check this first derivative at 3 pi over 2, I'll write that one out. Y prime at 3 pi over 2 is cosine of 3 pi over 2 minus sine of 3 pi over 2. That's this point on the unit circle, which has coordinate 0, -1. Cosine's first coordinate, so that's 0 minus a -1. That's positive. So if I'm looking at the transitions in that first derivative, I've got a positive tangent line, so I'll just draw a line with positive slope, negative slope of the tangent line, positive slope of the tangent line. That tells me that at pi over 4, I've got a max. And at 5 pi over 4, right here, I've got a min. So I've got a maximum at pi over 4, and we'll figure out what the second coordinate is in a moment, and a minimum at 5 pi over 4. And we'll figure out that second coordinate in a moment as well. Well, and the moment is here. I want the maximum of f. And if you are doing your reading, if you're religiously, scrupulously reading, you'll see those extrema, those are extrema for the function f. So I'm looking for the maximum of f. To find that point, I go back to the, or y. I go back to the original function y. I'll change those to y's because we don't have an f in this problem. I go back to the original function y to find that second coordinate. Sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is also root 2 over 2, and a couple of root 2 over 2's is just root 2. At 5 pi over 4, sine of 5 pi over 4, so I'm looking at y. Sine of 5 pi over 4 is negative root 2 over 2, so is cosine, and a couple of negative root 2 over 2's is just a negative root 2. So that's my information for my that I get from my first derivative. So now I'm going to shift us a little bit. And all right, we had already figured out what the second derivative was. It was negative sine of x minus cosine of x. And now we want to set that equal to 0. We want to set that second derivative equal to 0 to find places where the second derivative may change sign. Okay, so negative sine x minus cosine x. If that is equal to 0, I'll add one of those guys or the other to the right-hand side. It doesn't matter. And I'll get negative sine of x is equal to cosine x. And so you can just look at this as where are the sine and the cosine essentially the same size, but they differ in sig sign. Again, I'm going to draw up the unit circle. And right there at 3 pi over 4, and notice how important it is to have that trig on board. So if you're a trig teacher, if you ever ask your trig teacher, when am I ever going to use this? Probably they said in trig and in just about every other class you take in mathematics. So at the angle 3 pi over 4 and 7 pi over 4, we have the cosine ratio. It's negative root 2 over 2. Sine ratio is root 2 over 2. 7 pi over 4, we've got cosine ratio is root 2 over 2 because the x-coordinate's positive. Y-coordinate, however, is negative, and it's negative root 2 over 2. So this is where cosine of an angle and sine of an angle are the same size by the equality, but they're different signs. So to make them equal, you have to hit one of them with a negative sign. That's the two zeros in the interval. Remember, we're looking at in the interval from 0 to 2 pi. Always referring back to the directions. What were we asked to do? We're asked to graph this function over the interval from 0 to 2 pi. So now we have another real line and sine test situation, Siegen sine test situation, starting at 0 and finishing at 2 pi and putting myself some scale in between. I'm interested in these two places, 3 pi over 4 and 7 pi over 4. Those are the places where that second derivative is equal to 0. That is where this equivalent equation is true. 3 pi over 4 is a little bit bigger than pi over 2. It's right between these two guys. And 7 pi over 4 is bigger than 3 pi over 2. Thinking of it in terms of rotation, you rotate past 3 pi over 2 to get to 7 pi over 4. It's right in the middle of these two guys. And so now we just need to check the sign of the second derivative. And here's our note to ourselves. We want the sign of y double prime. We check the sign of the second derivative in these two intervals, from 0 to 3 intervals. 0 to 3 pi, 3 pi to 7 pi over 4, and then 7 pi over 4 to 2 pi. So let's just check here at this easy cheesy angle at pi over 2, which has coordinate 0, 1. Cosine is 0, sine is 1. So the second derivative, sine is negative, that'd be negative 1. So let's see, y double prime at pi over 2 is negative sine of pi over 2 minus cosine of pi over 2. That evaluates to be negative 1. So I get negative there. Y double prime at, I'm going to pick pi in this interval, is negative sine of pi minus cosine of pi. Again, I'm using that second derivative to check this Siegen sign. And sine of pi is 0, that's the second coordinate. And cosine of pi is negative 1, but I've got a negative 1. And so that ends up being positive. And then 7 pi over 4, you can pop in a calculator if you want. You could check at 15 pi over 8, which notice is almost 2 pi, but it's bigger than 14 pi over 8. You could check it in a calculator. I'm going to just kind of reason it out. That's about that angle right there. And negative, so the cosine coordinate is larger, and I've got negative sine of this angle. It's going to be a little negative number, and minus the cosine of this angle is going to be minus a positive number. That's going to be a negative number minus a positive number, which is going to be even more negative. Or just pop it in on your calculator. I didn't bring one with me here, so I'll just use some trig sense. And so what that tells me when you check the Siegen signs in those intervals is that on the interval from 0 to 3 pi over 4, our y prime, or y, is concave down. And here it's concave up. And on this little bit of the interval left, it's concave down. If we were asked, and we weren't, to give the intervals of concavity, we would say that this function is concave down on 0 to 3 pi over 4. As well as 7 pi over 4 to 2 pi. And we would say that it is concave up on the interval from 3 pi over 4 to 7 pi over 4. But what we notice is at these two places we have points of inflection because the concavity changes. The points of inflection are 3 pi over 4, comma, figure it out in a minute, and 7 pi over 4, figure out in a minute. A point of inflection is a point on the graph of y. So we go to the function y to figure that out. The original function y, if you recall, was sine x plus cosine of x. Sine of x at 3 pi over 4 is root 2 over 2. Cosine of x at 3 pi over 4 is negative root 2 over 2. Add those two guys together, they cancel, you get 0. And the same thing happens at 7 pi over 4, you get 0. So we know 2 points of inflection and we know our critical points. So let me put all of this together on a last slide for you. We're graphing over the interval from 0 to 2 pi. Again, putting in my benchmark points just for scale. And then we're also interested in what's happening at pi over 4, because that was one of our extrema. At 5 pi over 4, we had a point of inflection at 3 pi over 4, and notice how I'm relying on my trig sense to know where to place these things, number sense and trig sense. And our maximum was at pi over 4 root 2, so let's call this 2, let's call this 1, negative 2, negative 1. Pi over 4 root 2 was one of our extrema. Root 2 is about 1.4, so I'm going to just put that there. 3 pi over 4 was a point of inflection. 5 pi over 4 was a minimum, and we went as low as negative root 2 over 2. And then let's see, 7 pi over 4 was a point of inflection. And so we probably should figure out what this function is doing on the endpoints. Y is equal to sine x plus cosine x. If I want points on the graph, numerically, x and y coordinates, I'm going to use that function. At 0 radians, sine is 0, cosine is 1. At pi radians, just for benchmark purposes, sine is 0, cosine is negative 1. At 2 pi, sine is 0, cosine is 1, so I'm back up to 1 there. And I know I'm going to change concavity. I'm concave down on the interval from 0 to 3 pi over 4. I know this guy right here is a maximum. Change concavity to concave up. I know that 5 pi over 4 negative root 2 over 2 is a minimum. Still concave up until x equals 7 pi over 4, and then I change concavity to concave down. That's the graph of my function on the interval from 0 to 2 pi.